I just showed you that I can represent, and this was a conceptual jump from looking at the cell as a geometry, as an anatomy, to think about the cell as an electrical element. From anatomy to electricity. So this was the passive membrane model or circuit of a piece of membrane, patch of membrane, and I showed you that it is a very good representation just because of the behavior of voltage in response to current. It's a very good representation, an RC circuit, to passive small sphere of a cell, of a neuron. One thing I did not tell you, and I'm going to tell you now, that when one impales with an electrode into the cell, when I put an electrode inside the cell, I see something important, and this is that when I penetrate into the cell, I suddenly see a drop in voltage from 0 difference when I'm outside. Between outside and outside, the difference is 0. When I implant the electrode with an electrode inside the cell, I suddenly see a drop in voltage, and the cell is more negative than the outside. That means that if I would look at the voltage of the electrode while I am moving it inside the cell, when I get into the cell, suddenly there is a drop in voltage from 0 to something like minus 70 millivolts. This means that the inside of the cell is about minus 70 millivolt more negative than the outside of the cell. Always. The membrane sees, so to speak, negative voltage inside compared to the outside. And this is called the resting potential. Without any injection of any current, the cell is negative inside by minus 70 millivolt, and that's what is called the resting potential. So the cell always sits at rest, constantly, with a minus 70 inside versus outside. This requires energy, this requires pumps to make this charge distribution so that it will be negative inside compared to the outside. Otherwise, with time, the current will leak and will equalize the inside of the outside. And that's very important because every nerve cell in your brain starts always, not only in your brain, in any brain, always the inside is more negative. So this is our reference point. The reference is minus 70, sometimes minus 80, something on this order. Inside more negative. The cell is negative, is a negative cell, inside versus outside. This means that I have to add into my circuit another electrical element, a battery. So we should say that because of this resting potential of minus 70, I need to add a battery to my circuit. And this will signify a battery. And this short pole represents minus, and this longer pole represents the plus, or the more positive. So this means that the inside is negative compared to the outside, because the short pole here is the negative part. So this is the negative side. And this will be called the resting potential, E rest. So this is the full, complete circuit of this sphere, of this cell. It has the membrane has a property of RC, and also you have an initial condition, an initial state, the resting potential, which is about minus 70 more negative inside, and this is signified, this is represented by the battery. So this is the full circuit, and when I speak about depolarization, I mean relative to rest. Okay, so I start with the resting potential. Let's say that I inject the current here, I. Then I will get voltage response relative to rest, delta V, relative to rest. Okay, and I've stopped the current. I go back to the resting potential. Suppose now that I inject a negative current but in this case negative inside. This was injecting positive current inside. That's why I got depolarization. And now I inject negative current here. I will get hyperpolarization. So my voltage will become even more negative than the resting potential. And when I stop the current, I will go back to the resting potential. This is called hyperpolarization. Hyperpolarization, more polarization. Depolarization, less depolarization. So a positive current inside the cell will make the inside less positive. Depolarized. When I inject a negative current into the cell, I will get the inside more negative rather than minus 70, maybe minus 90. This will make the cell more negative inside. This I will call hyperpolarization. So this is the basic resting circuit. And when I inject current between the two sides of this circuit, depending on the direction of the current, I either get depolarization if this current is positive, and in this case I will charge the capacitance with positive current. This will be this case. This will be depolarization. If I inject a negative current, this will be this case, a negative current. Then I will get hyperpolarization, and in this case the inside will become more negative than in resting state. It will become more negative. This will be my hyperpolarization. And now you can understand that this cell is actually waiting, so to speak, for changes in voltage. It has a resting value, which is the reference value, determined by the battery here. It's always negative inside. And whenever it will get an injection of current, and I will soon tell you that those that inject current to cells are synapses. The synapses are the source of current. There are no electrodes in our brains, but there are synapses that behave like electrodes in some sense. These synapses will inject current into the cell, either positive current, then the cell will become depolarized, or negative current, then the cell will become hyperpolarized. So it can either grow from resting towards positive values or can become more negative than the resting, even more negative. And that's what the cell is really doing, moving the voltage constantly, depending on the activity of synapses that are source of currents. I will show you in a second, either moving the voltage, either charging the capacitance with plus, making the cell more positive than rest, or with minus. That's all that the cell is doing, at least as a first approximation. So in a second, we shall continue talking about synaptic inputs. Up until now, we spoke about passive membrane, and the input was extra current from the outside, which I called I. But as I said, there are no currents from outside in the brain. There are currents that are inside the cell, sources within the cell, the synapses. And so we shall speak about synapses in the next stage.